about liquid crystals and particularly on pneumatic wells, and I'm interested to hear about the three boundaries you have. Yeah.
So firstly, I'd like to thank the organizers for the invitation. So as you can tell from my title, I mainly work on the mathematical theories for pneumatic liquid crystals and the modeling of liquid crystals manufactured in industry. Now before I start, I have to apologize. There isn't really an analysis of free boundaries in my talk. But having said that, I do have a model liquid crystal problem at the end where there are interfaces, and I hope to describe this problem, and this might trigger some new collaborations, because for people who are more experienced with free boundaries and interfaces, it might give you an idea of the sort of problems we encounter in liquid crystal modeling. So I hope it will be interesting anyway. Now this isn't really a liquid crystal audience, although there are some liquid crystal experts in the audience, but so I thought the best way to start would be to actually very briefly tell you about what a liquid crystal actually is. And the simplest possible explanation is that liquid crystals, they are mesogenic phases of matter, or they are phases of matter which are intermediate between the conventional solid and liquid phases of matter. So they have physical properties which are somewhere in between. Now there are many different kinds of liquid crystals, as you might expect, but I work on the simplest kind, which are the pneumatic liquid crystals. And the easiest way to describe a pneumatic liquid crystal is to just simply say that pneumatics are anisotropic liquids. So these are liquids with special directions where the molecules, they flow about freely as in a normal conventional liquid, but while flowing they tend to line up, they tend to align along certain locally preferred directions. So these are liquids where the molecules have a certain degree of long-range orientational ordering. So the next question is, what makes pneumatic liquid crystals so exciting? In particular, why do I study them? And the key word here is probably anisotropy, because pneumatics, like I've already told you, these are liquids with some special directions, right? So they have different physical properties in different directions. They're anisotropic materials. But for example, they're optically anisotropic, birefringent, so they respond differently to light traveling in different directions. They're very sensitive to external electric or magnetic fields. They're also very sensitive to boundary treatments and surface treatments. And the key message here, the key message on this slide, is that it is relatively easy to manipulate a pneumatic liquid crystal configuration because of their susceptibilities. And because of this, because of their anisotropic properties, their anisotropic physical properties, this anisotropic response, optical anisotropy, anisotropic response to external electromagnetic fields, and mechanical responses, they have a wide range of applications in science and technology, as you might expect, and notably they form the backbone of the multi-billion-dollar liquid crystal display, the LCD industry, and I expect most of you have heard of an LCD. Now a large part of this talk is motivated, it's not directly relevant to, but it is motivated by the modeling of liquid crystal displays, or LCDs. So I just want to spend a couple of slides describing the basic working principle of an LCD. Now, pneumatic liquid crystals have two key properties which make them invaluable working materials for LCD applications. Firstly, they're optically anisotropic, which just means that they respond differently to light traveling in different directions. And secondly, they're very sensitive to external electric or magnetic fields. Now, any viable LCD must have two key properties in order for it to be realistic. The first property is that it has to support a bright and a dark state. There has to be a state which allows light to pass through, and there has to be a state which is opaque to incident light. And the other key property is that you must be able to switch between the two different states. So you must have at least two different states, and you must be able to switch between the two different states. So here I have a picture of the very commonly used, in fact a very basic LCD, the twisted pneumatic device. As you can see from the picture, the construction is very straightforward. You just have a layer of liquid crystal material sandwiched between two solid surfaces, very simple. Now both the surfaces, they are treated to induce a fixed orientation on the two surfaces. So they're rubbed, they're treated so that the molecules in contact with the surfaces, they have a fixed orientation on the two surfaces. And they're treated so that the two fixed orientations are perpendicular to one another. So in the absence of an electric field, which is the picture on the left, the molecules, they twist uniformly between the two plates. And this twisted state, it allows light to pass through, it is transparent. But then when you apply an electric field, the molecules want to line up with the electric field. They become more vertical, and this vertically aligned state, which is the picture on the right, does not allow light to pass through. It is opaque. So you have a bright state and you have a dark state. Now the only problem is that when you remove the electric field, this device just spontaneously relaxes back into the twisted transparent state. So there are two states, the bright and the dark state, but it is only the bright transparent state which is stable without an electric field. So this brings me on to a new generation of LCDs, which are bistable LCDs. And as the name suggests, the main idea here is that the geometry has multiple stable optically contrasting states. So from a practical point of view, both the bright and the dark states, they are stable without an external electric field. So you only need power to switch between the different states, but not to maintain each state individually. And clearly this is a very good thing, right? If you have a device with a static image, because you don't actually need power to maintain the image, you only need power to update an image. So if you can do this properly and successfully, it is a step forward. Now this brings me to the main subject of this talk. Now this talk is really about modeling of, well, it's a bistable LCD using PDE based methods. So this bistable LCD is what we call square or rectangular wells. It's a fairly simple geometry filled with a nematic liquid crystal material. Now this device was first reported in a paper by Sakonas, Davidson, Brown and Mottram way back in 2007, and they refer to this device as being the planar bistable LCD, a planar bistable LCD. I don't think this has actually been used in a commercial context yet. It's more of a theoretical thing, but it was actually experimentally manufactured and reported in this paper, and they refer to it as the planar bistable device. As you can see from the picture, the basic construction is fairly straightforward, right? You just have a periodic array of square or rectangular wells which are filled with nematic liquid crystal material. Very simple geometry. The wells are fairly shallow. This is quite important from a modeling point of view, which just means that the height of the well is very small compared to the cross-sectional parameters. And the other thing that you need to take away from the slide is about the boundary conditions. So the well surfaces, so there are at least 5 surfaces, right? The 4 lateral surfaces and the bottom surface. They're treated so as to induce tangent or planar degenerate boundary conditions. And all this means is that the liquid crystal molecules in contact with these surfaces, they have to be in the plane of the surface. They have to be tangent to these surfaces. Now let's just think a bit more about these boundary conditions, what they actually might mean in terms of the structure. So as an example, let's look at the bottom cross section, which is the surface, say z is equal to 0, so, and that's just a square, right? It's the bottom cross section. So you have these tangent boundary conditions, and what it actually translates to is that the molecules in the interior of this square, they are free to rotate in the plane of the square, but they have to be in the plane of the square. They're free to rotate. There's no single distinguished direction within the square, but it has to be in the plane of the square. But therefore on the edges, it's constrained to be tangent to the edges, right? For example, if you're on a horizontal edge, the molecule can either point this way or that way. It has to be parallel to the edge. Similarly, on the vertical edge, you can either point upwards or downwards. It has to be tangent to the edge. So there is naturally some sort of a mismatch at the corners, and this is where you would expect to see some sort of a defect or a singularity, but I'll talk more about that later. But you would expect to see something interesting near the corners. That's the only thing I'm trying to say here. But what is really interesting is that this very simple geometry is experimentally bistable. It has at least 2 different stable states. There are actually more, as you will see later in the talk, but experimentally they did find at least 2 different stable states. The first state is what they call the diagonal state. As the name suggests, here the molecules, they just roughly align along one of the square diagonals. It can be either one, but it just roughly aligns along one of the square diagonals, and you have these 2 radial defects at the, maybe say, the bottom left and the top right corner, but effectively it's just a nice diagonal profile where the molecules roughly want to line up along one of the square diagonals. The second state is what they call the rotated state. Here the molecules, they roughly rotate by 180 degrees between a pair of opposite edges. So for example, in the picture here, for example, it's rotating by 180 degrees between the bottom and the top edge, and as a consequence the molecules are more vertical. They're pointing up more or less upwards in the square interior, and they call this the rotated state. But what is important from a practical point of view is that both of these states, experimentally and numerically, they have long-term stability without an external electric field. And as far as the modeling and the experiments show, they also have different optical properties. So you have two different stable states, both of which have long-term stability. They have different optical properties, and hence this was a good thing for them. It's a nice bistable device. Now we've modeled this device within the Landau-Dijen theory for nematic liquid crystals. Some of you know that the Landau-Dijen theory is probably one of the most powerful continuum PDE-based theories for nematic liquid crystals. It was probably one of the reasons for awarding Dijen the Nobel Prize in 1991. Now, as is common in most phase field theories, the Landau-Dijen theory, it describes the state of a nematic liquid crystal by a macroscopic order parameter, which is known as the Q-tensor order parameter. And informally speaking, the Q-tensor order parameter is just a measure of the degree of anisotropy in the liquid crystalline system. It's just a measure of the degree of anisotropy and how anisotropic is the nematic liquid crystal. But from a mathematical point of view, we take it to be, this is the common convention, we take it to be a symmetric, traceless 3x3 matrix. You can see from this representation here, there are 5 degrees of freedom, and the idea is that this Q-tensor order parameter contains information about the degree of orientational ordering and the directions of preferred molecular alignment within this matrix structure. So like I've just said, the Q-tensor order parameter is a symmetric traceless 3x3 matrix. So from the spectral decomposition theorem, we can write it down in terms of its eigenvalues and eigenvectors, fairly standard. So this is what I have there at the top. So here lambda 1, lambda 2 and lambda 3, they are the eigenvalues, n, m and p are the eigenvectors. From a physical point of view, n, m and p, they contain information about the directions of preferred alignment of the molecules, and the eigenvalues contain some information about the degree of orientational ordering, all fairly intuitive. But what is important here is that nematic liquid crystals, they're broadly classified into 3 main classes, and this is important for the rest of the talk, according to the eigenvalue structure of the Q-tensor order parameter. The first case is what they call the isotropic case. The isotropic case is when the Q-tensor order parameter has 3 equal eigenvalues. But it's a traceless matrix, right? If you have 3 equal eigenvalues, all eigenvalues are actually 0, and the Q-tensor itself is 0, so the liquid crystal has lost its orientational ordering, it's in the disordered isotropic phase. The second case is the uniaxial case. Here the Q-tensor order parameter has a pair of degenerate, which means equal, non-zero eigenvalues. So you can write it in this concise form here, which is the second formula on the slide. I'll be quick here, but all you need to remember is that for a uniaxial case, n is the single distinguished direction of molecular alignment, in the sense that all directions perpendicular to n are physically equivalent. Uniaxial means single, and the minus 3 lambda, if you like, is like a scalar order parameter. It's a measure of the degree of ordering, orientational ordering about this single distinguished direction n. But uniaxial effectively means one preferred direction of alignment, and then you have one scalar order parameter to measure the degree of order about this direction. And the third case, which is maybe the most generic, is the biaxial case, where the Q-tensor order parameter has 3 distinct eigenvalues, and effectively there's a primary and a secondary direction of molecular alignment. So it's all as the name suggests. Now the Landau-Dijen theory is a variational theory, so there is an associated Landau-Dijen energy functional, as in most problems in the calculus of variations. As you might expect, the energy density is a nonlinear function of the Q-tensor order parameter and its spatial derivatives. Now for the purposes of this talk, you can make it more sophisticated, but I think the qualitative conclusions would be relatively unchanged. But for the purposes of this talk, I am really going to work with a very simple Landau-Dijen energy functional. So if you look at my formula, the top formula, the energy density just has 2 separate contributions. The first contribution is what we call the bulk potential Fb. So if you look at the formula for Fb, you will see that it's just a degree 4 quartic polynomial in the Q-tensor invariance, in the eigenvalues of the Q-tensor order parameter. You don't need to worry too much about this, but B and C, so there are 3 parameters here, right? A, B and C. B and C are just fixed positive material dependent constants. I don't do anything with them. The A is a measure of the temperature. So you can just think of A as being the rescale temperature. And the whole purpose of Fb is to drive the isotropic nematic transition, is to drive the transition from a disordered isotropic phase to an ordered nematic phase. So Fb likes to be in a disordered, or the minimizers of Fb are the disordered isotropic phase for high temperatures, and FB likes to be in an ordered nematic phase for low temperature. So it just drives the nematic isotropic transition as a function of the temperature. And the second component, W, is just an elastic energy density. So it penalizes any spatial inhomogeneities in the system. There are different forms of W, but for the modeling that we've done, we've just worked with forms of W which are quadratic and convex in grad Q. So one example, classical example, is just grad Q squared, sum of the squares of the first derivatives of the Q tensor. That's the simplest one, but you can work with maybe some other ones, like the one I have here at the bottom, but the qualitative conclusions are not heavily dependent. There might be some differences, but the qualitative conclusions are pretty much the same, as long as it's quadratic and convex, as long as it has a reasonably nice quadratic form in grad Q. And clearly what we are really interested in is computing the minimizers of this Landau-Dijon energy in these geometries subject to the tangent boundary conditions, because these minimizers, in our terminology, they correspond to the stable, physically observable configurations that you'd actually see in an experiment. So the talk is really about computing minimizers of this Landau-Dijon energy in these geometries. So moving on to the modeling details, we're not the first people to model this device. There have been several attempts before, but most people just typically treat this to be a two-dimensional modeling problem. So they just really look at what's happening on the bottom surface, which is z is equal to 0. So they really just look at what's happening on this square. But we've gone a step further. Our modeling domain is not a square. It's actually a rectangular box. It's a cuboid. So it's a 3D domain that we have. And if you look at our parametrization of the Q tensor at the top, we have retained all 5 degrees of freedom. So we haven't used any dimensional reduction. But we have made one assumption, which is quite important, but again I think the qualitative conclusion picture is unchanged. The wells are shallow, so even though we retain all 5 degrees of freedom, we assume that all variables only depend on the x and y coordinates. They're independent of the vertical z coordinate. So it's like a quasi 2D model. It is a 3D geometry, it's a 3D parametrization, but we assume that all variables only depend on x and y, they're independent of z. That was one point. The other point we have to be careful about is how we implement the tangent boundary conditions. So we actually have a closed rectangular box. And the way we've done it is on the lateral surfaces we work with Dirichlet boundary conditions, which are the two Q's that you have at the bottom. So it's pretty much fixed boundary conditions on the lateral surfaces. We can play around with that. And on the top and bottom we've effectively just imposed natural boundary conditions, and that seems to work. So all we do is we minimize the Landau-Dijon energy in these rectangular boxes with these boundary conditions subject to different initial conditions and see what happens. So we've done that, and what we find is a pretty crucial distinction between large and small wells. And I'll make this precise in a minute, but here I have a large well in the sense that the bottom cross section is on the micron scale, so it's fairly large. And what we effectively have here is just the diagonal and the rotated states that you saw in Mottrom's paper, right? There's nothing really new here. If you look at the director profile or the profile of the leading eigenvector, you have the diagonal state on the left and you have the rotated state on the right. There's nothing really new here. And you can also play around with the boundary conditions. For example, you can replace the Dirichlet conditions by, say, a surface energy, but that doesn't seem to change the picture too much. As long as you have relatively strong anchoring on the lateral surfaces, you do recover the diagonal and the rotated states for relatively large micron-sized wells with nothing really new. So now let's try and make these wells smaller and see what happens. But before I do that, I need to make the concept of large and small more precise. So what we do is we sort of measure the cross-sectional length in units of a material-dependent length scale, which the liquid crystal people call the biaxial correlation length, which I've denoted by xi b here. It's just a material-dependent length scale. So we now start to measure the cross-sectional dimension in units of xi b, because that's one way of making precise what is large and what is small. The next quantity we introduce is the biaxiality parameter beta squared. It's just a definition in terms of the eigenvalues of the Q tensor. The main point here is that beta squared is 0 for a uniaxial state and is non-zero for a biaxial state. And here I have a picture of beta squared, the profile of beta squared on the bottom cross section for a large micron-sized well. And as you can see from the picture, it's almost, so when you're dark, beta squared is equal to 0. Uniaxial is the dark regions, and the lighter regions are regions which have enhanced biaxiality. There should be a color shade here, but there isn't. But dark is uniaxial and light is when beta squared is non-zero. And you can see from the picture that is really roughly uniaxial almost everywhere. And you have these little biaxial lobes near the vertices. And why is that? Well, if you remember, we have these Dirichlet boundary conditions on the lateral surfaces. And the way we've done the modeling is that we have enforced Dirichlet uniaxial boundary conditions on the edges. So the liquid crystal has to be in a uniaxial state on the two edges. But these are two different uniaxial states, and the system mediates between the two different uniaxial states by this continuum of intermediate biaxial states, which are these little light colored lobes. And that's all that's happening here. It's constrained to be uniaxial on the edges just because we've enforced the Dirichlet uniaxial boundary conditions, but these are two different uniaxial states, and the system rotates between the two states by this biaxial lobe, this continuum of intermediate biaxial states. But for all practical purposes, this is just the diagonal and the rotated state with some extra information about the biaxiality. Now try and make the wells smaller. So it's kind of shrinking the well. There isn't really a scale here, but the point is at the top you just have the diagonal state with these little biaxial lobes localized near the vertices, and then you start shrinking the well, you start making them smaller. And what happens is that these biaxial lobes, they start getting larger, and then they start to overlap. And at a critical value, which we have quantified numerically, which is the top right picture, these biaxial lobes, they actually connect. And what you find is this, if you look at the light colored thing, is a two-dimensional star-shaped biaxial ring which is connecting the four vertices. It's a global biaxial profile. So right along the square diagonal is perfectly dark. So it's perfectly uniaxial along the square diagonal. If you look at the top right picture, it's perfectly uniaxial along the diagonal. It's perfectly uniaxial along the edges. But in the middle you have this light-colored star-shaped biaxial ring. So it's a global biaxial profile, and this is a new state which was not previously reported in any of the literature, presumably because you are making the wells pretty small, right? Because we get this critical phenomenon at eta is equal to 7, but if I translate it into dimensional language, it's really something like, I don't know, maybe 30 nanometers or something, or maybe 50 nanometers. So it's pretty small. You'd have to make the wells pretty small to see this, but this was not previously reported, and we've called this new state the well order reconstruction structure. And here we've just probed a bit more. So I'm being fairly informal here. Things are not giving you the exact dimensional quantities, but just a flavor of what's actually happened. But here this is really just a plot of the biaxiality parameter along a square diagonal. So if you look at the black line, you can see these two well-separated maxima. And this is really the diagonal state which Mottram had in his paper. And you have these two well-separated maxima because you have these two well-separated biaxial lobes, one for each vertex, right? Because you're plotting the biaxiality parameter along a square diagonal, and the biaxiality profile has two maxima, one for each of these localized biaxial lobes. There's a maximum for each of these biaxial lobes. But this is just the diagonal state. Now you make the wells smaller. These maxima, they start to come closer together. Then they merge, you get a single maximum. Then you make it even smaller. You find that the maximum of beta squared, if you look at the first three, the black, the red, and the blue, the maximum value is 1. But as you make the wells even smaller, you can see that the maximum value is getting suppressed. It's getting much less than 1. And then there's the critical value, which is our new well order reconstruction structure, where beta squared is actually 0 along the square diagonal. And that's the signature of the onset of the WORS. And it's actually the unique observable state for all wells which are smaller than this critical well size. So the main idea here is that you make the wells progressively smaller, there's a critical length, and for all R less than this critical length, you only really get this well order reconstruction structure, which is a global pattern. Now I want to quickly finish with a problem where you actually see interfaces. So this is a paper by a group in Lisbon, Tello da Gama. As you can see from the picture, again, their construction is not so dissimilar from ours. They just have a layer of liquid crystal material between two surfaces. The top surface is nice and flat. The bottom surface is featured by periodically spaced rectangular grooves. It's a 3D geometry, but they've really modeled the geometry in 2 dimensions. In terms of dimensions, they measure everything in units of a material-dependent length scale, which is the nematic correlation length psi. Regarding boundary conditions, they have free boundary conditions at the top, but on the rectangular grooves, they have normal boundary conditions, which just means that the molecules want to be normal to the edges of the groove. That's fine. But what is crucial here is that the modeling is done at the nematic isotropic transition temperature, right at the transition temperature, which means that the isotropic phase and the ordered nematic phase, they have equal energies. So it's actually energetically viable to have phase separation and have an interface between the two states. So they've modeled this. This is all numerical modeling. And as you can see from the picture, they have at least 6 different states. And these states, they are really just distinguished by what the nematic molecules are doing inside the rectangular grooves, and also the shape of the interface which separates the isotropic and the nematic phases. So if you look at the picture, the purple or the blue bit is what they call isotropic, and the colored bit, the yellow bit inside the rectangular grooves is a nematic phase. Now the first one, the bent, you can see that the molecules are roughly bending by 90 degrees near the 2 bottom corners of the rectangular groove, and also the interface is bent but is sharply pinned. The second one is the splay bend. Here you have a radial profile near one of the corners and you have a bend profile near the other, but the interface is flat and still pinned to the 2 corners. The third one is the splay. You have a radial profile near 2 corners and the interface is still flat. So there is a distinction in the shape of the interface and what the molecules are actually doing inside the rectangular groove. So these are the 3 key states they observe. Don't worry too much about the states with the tildes. They're really just a variant of the first 3. And they're not really relevant to this talk. Now, what they have done is that they have solved the full nematodynamic equations, the full dynamic equations using a lattice-Boltzmann method, including a fluid flow. And it's it's computationally quite expensive, it's very complicated. But I think, and I have said this to them as well, that you can actually recover the qualitative details using a simpler approach, a much simpler approach. Basically a 2-dimensional modeling approach, and you just take a Q-tensor order parameter. The key quantity of interest is this scalar order parameter S, and you just minimize the Landau-Dijon energy inside these rectangular grooves subject to these normal boundary conditions, and we can think of this interface as being the 0 set of S, and we just track the 0 set of S without all this additional complication of the full dynamics. And I think this would actually give them some insight into the interface itself. And also you can use I propose that we could probably use a gradient flow approach to actually study the evolution, the interfacial dynamics, and that's quite standard. So you use a gradient flow approach for the Landau-Dijon energy. It's quite fairly straightforward to write down the equations. So here I have a PDE for the scalar order parameter S, and you solve this PDE subject to the boundary conditions, because you do have normal boundary conditions on the rectangular edges and a suitable initial condition. And that should give us some qualitative information about the interfacial dynamics. And they have investigated it numerically, and they do find interesting transitions between the different states. So I think I'd like to stop here, just saying that this is a nice new modeling problem, and if people want to talk more, then I'm very happy to speak to you. Thank you.
Well, thank you. Are there questions from the audience? I had some questions about your the boundary conditions. Actually, I have 2 questions. The boundary conditions, you have singularities at the corners, right? And how can I never understood how can you model this 2-dimensional, because it's inherently 3-dimensional.
Well, you can do it. So it's the S, right? So you can construct Dirichlet conditions, which would, so for a singularity you construct a Q. So say you want Dirichlet boundary conditions, and you also want to incorporate the singularity. So for example here, I have an N somewhere. I have an N and an S. So the N will be singular at a vertex, but you can combat this singularity by hand by constructing an S which will vanish at the corner, which is why the interface or the defects in a 2D problem, in some sense you track the 0 set of S.
But you do that somehow more or less artificial.
Yes, yes. And if you go to 3D, you find, what I found is that you get these biaxial lobes instead of something which is it's not really isotropic. For any reasonable temperature closely, you would find some biaxiality.
And And the other question was the boundary condition. How easily can you maybe change the boundary conditions to get completely different states, right?
Experimentally or?
Yeah, and of course you can,
Yeah.
theoretically I think you can do this, but maybe they're
I think
changing the anchoring, or if it's
they do.
strong, or you know.
I think they use polymers to rub the surfaces, or they treat it with laser and.
But you can.
Yes,
do
I
this
think the
thing.
answer is yes.
So because this is one set of boundary conditions where you can get various different states, but you could probably produce all kinds of other.
Yeah. I think the answer experimentally is yes. But
Okay. And what is it good for? So in applications,
you mean teledogammas?
you get these new states, for example.
You get these new states and you have this interface. I think for them the dynamics is important because it's because dynamics for them, they induce dynamics by applying an electric field. So if they know exactly how the interface responds to an electric field, in some sense they want to compute the optimal transition path between the different states, because that might correspond to a minimal voltage, and if you had a device based on this thing, then that would be the most inexpensive route of switching. That's how they're motivated.
Okay.
So you sort of answered this question, but the biaxial lobes, I mean, if you took a large cell, I mean, how large would the biaxial lobes coming from a one of these, 10 nanometers or something?
It's of the order of the biaxial correlation, and so yes, 9 to 10. I mean, depends on the material, right? Because there are some materials which have an intrinsically larger correlation length. If you had a polymeric liquid crystal, it would be 10 times larger. But my standard answer is about.
It's about 5 or 4 or 5 molecular lengths.
Yes.
So in any of these situations, has in fact the biaxial state been observed experimentally?
You mean the biaxial lobes?
Well, but biaxial, I mean, biaxial anywhere actually, in any of these
Well,
experiments.
if you have a micron-sized cell, and if biaxiality is indeed so heavily localized as these pictures suggest, then for all practical purposes, it's not going to. I mean, I think beta squared is strictly non-zero everywhere, right? It's just very small. When we say uniaxial, we just mean it's very small. And yes, you have these regions of concentrated biaxiality which are of the order of maybe 5 to 10 molecular lengths near the vertices. For all practical purposes, for an experimentalist, it's not going to change things very much. So I'm not surprised that they don't actually report biaxiality, and which is why they're quite happy with the 2D model, as long as it gives them the director.
Okay. We're behind, so any further questions, please in the coffee break. So let's thank Apala again for the